Phase shift, sinusoidal curve fitting. So chapter 6, section 6. Okay, so up to this point, we have dealt with graphing our trigonometric functions, but we've just dealt with amplitude and period. Now what we're going to do is we're going to add in phase shift. Now we could technically add in, a vertical shift of some sort too, but I think you should be able to figure that out, that if you go through this whole sinusoidal function and then you add a value to it, it just shifts the whole thing up by that amount. So let's take a look at this. So amplitude, period, and phase shift. So for the graphs of y equal to a sine of omega x minus phi, or y equal to a cosine omega x minus phi, we will do the following. And yes, sometimes that is referred to phi, sometimes that is referred to phi as phi. That little thing that looks like a null set, that is either the Greek letter phi or phi, and it really is an argument that's gone on for a very long time between mathematicians and engineers. So call it whichever you will. Here at MVCC, there's phi theta kappa, phi, yet being an engineering student, I always came through learning it as phi. So you're going to have to live with that. So first of all, the amplitude is A, just as it was before. Your period is still going to be 2 pi over omega. The only difference now is that your phase shift, that's your shift right or left, is phi over omega. Now remember, if we had x minus phi, we would just say, okay, well, that's shifted to the right by phi. But since we have omega x minus phi, we have to divide that omega out of phi to get our phase shift, because remember that omega is changing our period. So our phase shift has to be adjusted for that. So let's just go through it. I think you'll see it as we go through an example. So y is equal to 3 sine 4x minus pi over 2. So first of all, the amplitude is 3, omega is 4, therefore our period is 2 pi over 4 or pi over 2. Oh, I'm sorry, our phi is pi over 2. Got ahead of myself there, just pulling out those pieces. Our period is 2 pi over 4, which is pi over 2. Our phase shift is going to be pi over 2 over 4, which is pi over 8. So now that we have that, we can start drawing this. So just as we did before, we're going to say, well, the period is pi over 2, so let's put that there. Half of that is pi over 4, half of that is pi over 8. And then halfway between pi over 4 and pi over 2 is 3 pi over 8. And I can start plotting my sine wave. So it's 0 up to 3, down to 0, down to negative 3, up to 0. And there's my 3 sine of 4x. But now I have to account for this phase shift. I had that phi of pi over 2. So my phase shift is going to was pi over 2 divided by 4, or pi over 8. Since it's minus, it's shifted to the right. So I'm just going to take my graph and I'm just going to move it to the right by pi over 8. And that's all we have to do. So we're going to draw our sine wave or our cosine wave just the exact same way of finding the period, breaking that up to the 5 points, right? 4 equal pieces, but breaking up into the 5 points, going half, half, and then getting the in-between one, plotting those 5 standard points, and then moving it right or left according to the phase shift. So not much different than what we were doing. And that's graphing them. So now let's go a little beyond that. Steps for fitting a sine function, y equals a sine of omega x minus phi plus b to data. Now remember I said that if we added something on afterwards, that would give us a shift up or down. So that's what we're kind of throwing in here. But what are we talking about here? We're talking about having a bunch of data. So not just having the actual function, but being given a bunch of data and trying to fit that data to a sine function, or coming up with a sine function that approximates that data. Think of it as sinusoidal regression. You've dealt with linear regression, you've dealt with quadratic regression. Well, now we're dealing with sinusoidal regression. So first, determine A, the amplitude of the function. And remember, we're coming off the data. We're not looking at the equation for it. We're coming off the data. So the amplitude is equal to the largest data value minus the smallest data value, right? Max to min divided by 2, because amplitude's from the center vertically to the peak. So maximum value minus minimum value divided by 2 gives us our amplitude. Determine B, the vertical shift of the function. Okay, the vertical shift is that center point vertically. What had to, because if there's no shift, that would be 0. So whatever our center point vertically ends up being, then that's going to be our vertical shift. So that's the largest data value plus the smallest data value divided by 2. So basically we're averaging our min and max. If our min and max are equal and opposite, 5 and -5, then you're going to come out with 0/2 or 0. If there's any sort of vertical shift, this is going to give it to us. So subtract the largest value minus the smallest value and divide by 2 gives you your amplitude. Add the largest value plus the smallest value and divide by 2 gives you your vertical shift. Then determine omega. Since the period t, the time it takes for the data to repeat, is t is equal to 2 pi over omega, we have omega is equal to 2 pi over t. So all we did was we solved that t equal to 2 pi over omega for omega. So 2 pi over t. So we look at it and say, well, what's the period? And we're going to take 2 pi divided by that is going to give us omega. Then determine the horizontal shift of the function by using the period of the data. Divide the period into 4 subintervals of equal length. Determine the x-coordinate for the maximum of the sine function and the x-coordinate for the minimum, for the maximum value of the data. Use this information to determine the value of the phase shift. Okay, so we got x-coordinate for the maximum of the sine function. Where should that be in this period, right? And the x-coordinate for the maximum value of the data. So now we're trying to match up, where do we expect the peak to be in sine? Where do we see it in our data? And the difference between that is the phase shift, phi over omega, which means we can find phi by taking that shift and dividing it, well, and multiplying it by omega, which gives us phi. So let's look temperatures in Syracuse, New York. So the data table shows the highest daily temperatures in degrees Fahrenheit averaged over the month for the cities of Syracuse, New York, Washington, D.C., and Austin, Texas. So we got this table of data here, and we're going to look at Syracuse. So you can see that we've got months here, and we numbered them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because we're going to graph it, we need numbers. Okay, and we have these temperatures associated with them. So the highest daily temperatures averaged over the month. So basically, January, you have 31 days. Each day, they took the highest temperature of that day, and then they averaged those 31 temperatures and got the highest daily temperature averaged over the month. Okay, so we've got in January, the high was 32, February 34, March 43, April 57, May 69, et cetera, et cetera, et cetera. So we've got this whole thing here, and we're going to work through our steps. So the first thing we're going to do is we're going to find the amplitude. So we're going to take the highest value and subtract the smallest value. So the highest value was 82 in July, and the smallest value was 32 in January. Well, I can tell you one thing right here that's nice to see is the fact that we have 12 periods of data, right? January, February, March, 12 months. And the difference between the peak value and the minimum value, the maximum value and the minimum value for those months is 6 months. July was 82, January was 32. That's a 6-month difference. So 82 minus 32 divided by 2 gives us 50 divided by 2. Remember, order of operations, please, right? This is 82 minus 32 gives you 50, then divide by 2, not 82 minus 32 divided by 2. Okay, so just be careful about that when you plug those things in your calculator. So we get 50 over 2 or 25. Now we can find the vertical shift by adding the max and min values. 82 plus 32 is 114, divided by 2 is 57. So we're shifting up by 57. So we've got our A, we've got our B, which is our vertical shift. Generally, the way we're doing it is we're basing it on the sine function. So we know sine. So all we need to do now is we need to find omega and phi. So the period is 12, right? We got 12 months. Omega is equal to 2 pi over the period. 2 pi divided by 12 is pi over 6. So we have our omega. The peak is at 7. Remember, we're going to look at where did the data peak and where would we expect the peak to be in our sine wave. Well, remember, the sine wave peaks at the first quarter of the way in. So if we have 12 months divided by 4, that would give us 3. So we would expect our peak to be at 3. Instead, our peak is at 7. So we have a phase shift of 4 to the right. So if our phase shift is equal to 4, then we multiply that by omega, which is pi over 6, which gives us 4 pi over 6 or 2 pi over 3, and that gives us phi. Now that we have our amplitude, our omega, phi, and b, we can put the equation together. So we have y is equal to 25 sine of pi over 6x minus 2 pi over 3 plus 57. And I understand there was a lot to that went through a number of things, but it's very straightforward, shall I say, because it's just the steps. Find the amplitude. Maximum minus minimum value divided by 2 gives you the amplitude. Vertical shift, average the maximum and minimum values. Determine the period of your data. Use that to find omega. Find where the peak is and where you'd expect to see it in a sine function. The difference between that's going to be your phase shift. Your phase shift times omega is going to give you phi, and then plug it into the equation. So this can be a very useful tool because now I have this function that allows me to predict what the highest daily temperature average over a month is going to be for any given month. And that's the power of these regression equations, or in this case, fitting our data to a sinusoidal function.